So, I touched on this a little bit already. This is a really cool idea here. So, the problem was, and still is, the problem was that we were talking no calculators, so some functions that people were working with, natural log was invented in about 1400s or so, exponential along with it. Trigonometry functions have been around for almost 2,000 years and so on. Now, these are all ugly. And if you'd asked a Greek to estimate sine of 30 degrees or something, he would have got some kind of measurement tool, actually measured the opposite side, actually measured the hypotenuse side, divided those two results, and that's the sine of 30, after measuring an angle of 30. They did it by calculation in grid. Now, obviously, there's a ton of measurement error in there, and so that wasn't very accurate. That said, then, trying to get a numerical or analytical way of finding these transcendental values was a big question of the day in Newton's time. How can we do a little better job of finding these things? Now, with the calculus, they started to have a little better results. It goes a little like this. The thought process went, well, man, I could estimate sine pretty well. I'll do sine, I think, is what I have in my notes. I could try and model sine well, numerically or graphically, by trying to fit polynomial to it, because polynomials are so much fun to work with, easy to work with. I can easily square stuff, cube stuff. That I can do with enough time, remember. So they did a ton of calculating by hand. So as a process, it went something like this. They're trying to create a polynomial function that matches the sine function. And they did it in steps. Now, notice first and foremost that the polynomial is written the opposite of what we typically do, which is in ascending order rather than descending power order. We're going to go from constant to linear to square to cube and so on. So the powers get bigger that way, and if they have a polynomial, and you'll see that's very common. All right, now imagine, first of all, if I'm going to make my polynomial fit sine, the first choice is, where do I want to fit it well? I could try and focus on making it fit well here at pi, or here at pi over 2, or somewhere in between, or 0. The most logical place to fit well is to center it around 0, right? Now, when you do that, that's actually called a Maclaurin polynomial. That's where you're a specific case, but we'll talk about that in about 20 minutes. For now, I'm going to try and fit around x equals 0. Now, if my polynomial is going to truly match the sine function, then first and foremost, they have to have that same point. Those points must match. Now, that means that the polynomial at 0 needs to equal f at 0. So they meet at 0, right? Alrighty then. That would imply that if I look at this and I plug in an x of 0, that would mean that a plus 0 plus 0 plus 0 is forever equals sine of 0. And from that I can conclude that that a is 0 in this case. So far so good? Okay. Now then, I know that needs to be nothing. That makes sense because the sine curve needs to go through the origin, so we don't want to wind up. Cool. Now, I want my polynomial to have the same slope as the sine curve there. Well, to have the same slope, that would imply I need my polynomial to have the same derivative at that point, right? Okay, so p prime at 0 needs to equal f prime at 0 in order for them to slope the same way there. Now, p prime at 0, that is b plus 2cx plus 3dx squared plus, if I did one more, maybe, what would the next one be, you reckon? 4ex cubed, dot, 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 dot. Now, I'm going to evaluate that at x equals 0. And that needs to equal the derivative of sine, which is cosine at 0. Now, although it seems like I'm getting a ton of terms here, because I'm using at x equals 0, all of these guys go away, and so I get that b equals cosine of 0, which is 1. At that point, I have that p of x is 0 for a, plus 1x, plus still don't know c, still don't know d, and so on. Follow? Okay. Now, really, in essence, we just found y equals x is a tangent line to the sine curve. If I just left everything else off, all the other polynomial terms. You with me? All right. Now, tangent line doesn't fit very well because of the curve. And so we would also, instead of just matching the slope, we would also like to match the concavity. We want our curve to have the same concavity as the sine curve. So that implies that the second derivative at 0 of our polynomial needs to match the second derivative at 0 of the sine slope. All right? Now, the second derivative is the derivative of that bad boy. What's the second derivative? 2c plus 6. I'm not going to call it 6. I'm going to call it 3 times 2. dx rather, sorry. Plus 4 times 3 ex squared plus, what would the next one be just for fun? 5 times 4 f, which would be a really terrible constant choice, but you get the idea. X cubed, dot, 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 dot. That's at x equals 0. That needs to match the second derivative of sine at 0. What's the second derivative of sine? Negative sine of 0. Now, that then implies that 2c is, you can see all the other terms in the polynomial go away because x is 0, right? So 2c is left, and it equals 0. Seems like we're dropping a term out every other time, all right? So at that point, p of x is 0 plus 1x plus 0x squared plus, then we're back to unknown territory, dx cubed plus ex to the 4th, and so on. All right, we're getting there. One more. Now, let's have them have the same third derivative, which is to say the same change in concavity. The concavity is changing at the same rate. That would imply that p triple, or the third derivative of p at 0, we want this to specifically be at 0, because that's our focus, equaling f triple at 0. W? Okay, what is p triple? Here's p double, looking back at our work. What's p triple? 3 times 2 times d plus 4 times 3 times 2 e times x to the first plus 5 times 4 times 3 f x squared, and so on. That'll be evaluated at x equals 0, and that needs to equal the third derivative of sine, which is cosine or negative cosine? Negative cosine of 0. That then, evaluated at 0, the polynomial drops out everything except for 3 times 2 times d, which is negative 1, and so d is negative 1. I'll call it negative 1 over 3 factorial. All right? So then, looking for maybe a pattern here, now instead of keeping with the derivative idea, at this point we're at p of x is 0 plus 1x plus 0x squared minus 1 over 3 factorial x cubed. Now then, what do you reckon here? If we tried to establish a pattern, what do you think x to the fourth will be? 0x to the fourth. What about the x to the fifth? Negative or positive? It's positive. It's alternate. Positive, negative. Positive, negative. 1 over 5 factorial x to the fifth, so on. Now, typically then when we write these, we don't write the zeros. I just wanted you to see the pattern. But if we drop the zeros, then we're talking x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on. Now, would you make sure that you put a plus dot dot dot? Did you know that on the AP test, if you don't have dot 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 in the correct place, you will be missing points? Okay, it is an infinite series. Now, this is called expanded notation. Students generally work better with expanded notation, but you also need to be familiar with summation notation, or writing the pattern to this. We typically start with an n of 1, although you could start with 0, I suppose. Okay? If you do, then x to the, yes?
So when you wrote p of x, how come it's plus x over 5 factorial and not top?
This is a 3. This guy?
No.
So where is it continuing on?
Right above.
You said
Oh,
put
here to
down
here.
there.
Good call. I don't know the. Oh, this is plus. This should have been plus. Sorry, it should have been alternating. Sorry. Thank you. Okay, it was supposed to be alternating. Okay. So x to the, what's the pattern to the powers? Odd. Based on it starting at 1, it should be 2n minus 1. Okay? What about, actually, you know what? I take it back. I want to start at 0. My bad. If I start at 0, we're going to go with 2n plus 1. Sorry, the more typical ways to start at 0. Okay? What else we got going on there? There's other parts to the pattern besides just the x. The alternating negatives. So that's negative 1 to the, based on it starting at 0, would we go n or n plus 1 in order to make sure that we started with the positive? If I go n and I start at 0, would that be positive? It would. Okay, so n is good because that would make a starting positive term. N plus 1 means we start with the negative. We don't want that. What about the denominator? 2n plus 1 factorial. Is that okay? No, it's not okay. It needs to be in parentheses. Okay, otherwise you're saying plus 1 factorial, not the whole thing. Okay, now then, fitting a series to a function is called a Taylor polynomial. After this Englishman wrote Taylor. So, now that's great. That worked great for sine, but we want to then typically go on to a more general pattern. So, instead of sine, consider this. Please, let's do a general Taylor series. I want to fit f of x, some could be sine, could be any, okay? Could be any curve, e, whatever. I want to fit any crazy function f of x with a polynomial function p of x. And I typically center it around 0. Oops, like I did over here. But it doesn't have to be centered around 0. I could try and start by fitting it around 3 or 7 or whatever. See, I'm going to fit my polynomial around x equals c. Now, a lot like when you do a tangent line, typically you do a tangent line in a kind of point slope form. So instead of x, you have x minus c kind of thing. You're going to fit a whole polynomial around c, and it's going to be x minus c everywhere, not just in a tangent line x minus c way, but everywhere x minus c way. All right, now, the goal is to first just do exactly like we did here. We want this idea is f of x is some crazy function, and I want to fit a polynomial well around c. And depending on the function, maybe we can get further and further out and fit it wider and wider, but we'll talk about that in a second. Now, if I want to, my red's going to be, if I want to fit my function here, the very first thing I want to have happen is that my polynomial has to have that c. And that is to say, just like here, p at c needs to equal f at c. I want them to have the same point there, point of tangency, I guess you can see it. Now, f at c, actually, let's go p at c, that's just, the right side was fine. P at c, look up at p here. If you put in a c for x, you would get a plus b times 0 plus, I have no idea, I guess, oh, I skipped over c, sorry. I didn't want to use c again, so you can see that that's really a d times 0 and so on, right? What that tells you then is that a must be f at c. So at that point, my polynomial, as far as what I know so far, is that that a has to be f at c. The other stuff, I still don't know yet. Are you with me? Okay. The idea is that I need to perfectly find these coefficients to make the polynomial bend and curve exactly like my curve does. You follow? Okay. Now then, I want to match the slope. If they have the same slope, then that means the derivative of the polynomial at c needs to match f prime at c. Wait. What is the derivative of p? A drops out and I have just b plus 2d x minus c plus 3e x minus c squared plus, if I wanted to keep going, 4f x minus c cubed, and so on. And that equals f prime at c. You follow? Okay. All right. So now, if we want to meet it at x equals c, we want the derivatives at x equals c to match. Well, at x equals c, b stays, but everything else, when you put a c in for x, drops out. And so b is f prime at c. Okay. At that point, my polynomial is f at c plus f prime at c times x minus c plus don't know d, x minus c squared plus don't know e, x minus c cubed, and so on. Alrighty. Well, next thing we do is match the concavity, which means what? Second derivative. P double at c needs to equal f double at c. Look back, here is p prime. Take the derivative, please. Have 2d plus 3 times 2 e times x minus c to the first plus 4 times 3 f x minus c to the second plus so on and so on and so on. Yeah? Now that needs to equal f double at c. Cool? If we then say add x equals c, then we get that familiar dropping out of everything with the x minus c still there. So I'd have 2d only, and everything else drops away, lots of zeros afterwards, equals f double at c. That means that d is f double over 2. So my polynomial is f at c plus f prime at c, x minus c, plus f double at c over 2 x minus c, plus some other stuff we still haven't come. Stop me if you're confused. It is squared, yes. Thank you. It is squared. Okay. Okay. Well then, let's do one more. I just want you to fully understand why the formula is what it is. If I take the derivative of p double, here it goes. P double's, so I can match p triple. Now I want to match p triple at c to f triple at c. We take the derivative of f double or p double. What's the derivative of p double?
3 times 2
3 times 2 times e
times 4 times 3 times
times plus 4 times 3 times 2 x f x minus c, right? Plus dot 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 dot, and that needs to equal f triple at c. When I put in x minus c or x f times f is I shouldn't have used that. Sorry, I should have used g or something like that. That's a constant.
Yeah.
Sorry. X is there. At x equals c, I get 3 times 2 times e plus a bunch of zeros equals f triple at c. Therefore, the third coefficient, or the fourth coefficient rather, is f triple at c over 3 factorial. Now, you can start to see the pattern. Obviously, if you didn't see it 20 minutes ago, I apologize. But it goes like this. The polynomial that fits some f of x around x equals c is, first of all, the point has to match, f of c. Next, the derivative has to match. Then the second derivative has to match, that's it. But you start to get this, as you took greater and greater derivatives, you had powers coming down each time and getting multiplied by the power that already came down. And you start to get this factorial pattern in the denominator. This is squared, darn it. Those denominator factorials come from when you kept bringing down powers and then dividing them over. So generally speaking, you would say the general term is the, I didn't leave myself enough room, the nth derivative at c times x minus c to the n over and factorial, and it continues on forever after that as well. That is how you find a Taylor polynomial. Now, let's do an example or two or 3 or 4. Ready? Okay, here we go. Imagine that I wanted to fit cosine, but instead of fitting it around 0, I wanted to fit it around pi over 6. The Taylor polynomial, I could call it p of x, some call it t of x. I don't care which one you call it, but it is f at c plus f prime at c, x minus c over 1 factorial, most people don't bother writing, c over x minus c squared over 2 factorial, and so on, right? They will typically ask you to write They'll tell you how much to write. I'm going to tell you write the first 4 terms. Okay? Sometimes they'll ask you to find the general term, but you'll see that the general term is a bit of a not happening here because there's not a pattern. Okay, so what's the function? Cosine of x. We're trying to match cosine of x. What's the center I'm trying to fit around? 5 or 6. Okay, so I have that clear in your mind. It's hard to find f of x or f at c if you don't know what f is or c is. F at c then is cosine of pi over 6, which is
Root 3 over 2.
root 3 over 2. Okay, plus f prime. What's f prime? Negative sine at c is negative sine of pi over 6. That is negative 1/2. X stays x. This is meant to be a function that works for any x you want. But c is c. What's c? Pi over 6. Okay, we're centering it. You could think of it as we shifted our whole polynomial over to pi over 6, right? X minus pi over 6 over 1. That didn't really necessary. What's f double? Negative cosine of pi over 6, x minus pi over 6 quantity squared over 2 factorial. So what is that looking like? Negative root 3 over 2 times 2 factorial x minus pi over 6 squared. Track it? It said first 4 terms. So the next term will be the last one. What's the derivative of negative cosine? Positive sine. We're back to positive sine of pi over 6. We're talking cubes now. So our last term is 1 over 2 times 3 factorial x minus pi over 6 to the third. You'll often see this written with a subscript. Now this, when a Taylor written with a subscript, usually is a reference to not how many terms. This is always a source of confusion. I mean, we're typically thinking n is how many terms. In a Taylor series, that represents the power at which you're going, or the degree. Okay? Taylor subscript represents ending power or greatest power. You would often hear this referred to as a third degree Taylor. You will be asked, find a third degree Taylor series for blah, blah, blah. You need to understand that means you go until you get to x cubed, and then you stop. All right? Okay, now, Taylor series then are all series. Taylor, centered around any C center. But if you specifically talk about letting C equal 0, or saying, I want to focus my Taylor around its origin, or around x equals 0, that's usually referred to as a Maclaurin series. A Maclaurin series is a Taylor series, but a Taylor series isn't necessarily a Maclaurin series. Are you with me? Okay then. It is. In college also, there are pretty much 4 big ones you need to know. And definitely on the AP test, you're expected to have 4 Taylor series and Maclaurin series down cold memorized. That'll take a while, but you'll just... Okay, they are sine, which we just did, but also cosine. Would you please find the Maclaurin? Do you feel like you can try one on your own? Or do one more? Would you, I think you can tackle it. Would you do the Maclaurin series, or try the Maclaurin series for cosine? When I say Maclaurin, that means that C is 0 when you go to write your table. stuff. F at 0, F prime at 0, F double at 0. We need all those. I'm going to show lots of work. You don't necessarily have to show all this work. I would like you to give me the first 3 non-zero terms and the summation notation. Actually, I'm going to take that back. I require the first 3 non-zero, the general term, which is to say just with a general n in it, and then summation notation. Is it going out, or you're flailing around madly and going? Trying to see what Ms. Cannon did not teach this earlier. It's hard to do this if you barely see the derivative of sine or cosine. You need to have those skills just automatic. Why our book puts it so early, I have no idea. How are we doing? Are we ready to go over it or not yet? Not yet. You have the first 3 questions before you go do anything else.
Yes.
Okay.
What do you do like this one?
What do you do?
Or are you saying like why would you do that?
Oh, yeah, good question, because it's not funky.
Yeah.
It's a great question. I love that question. I'll answer it in a minute. Okay, so how are we doing? General term? Now, general term is a ton of overlap with the summation notation. You're kind of writing a formula, all right? It's just not in the summation. You don't have to sweat the original x, but x to even powers. How do you make even powers? Given any input of a whole number, 2n. 2n makes evens, so no matter what you put in, when you double it, it'll become even. 2n factorial is the same in the denominator, but there's also an alternating negative 1 to the. Now, if I use 2n there, what's the implication about n starting point? 0, right? Do you agree? Okay, so it must have started at 0. So do I want here, maybe I should have done 0 on the sign. Dang it. Do I want to n here or n plus 1? N. Okay. Now, once you've got that, then the summation notation is very much the same. Notice, by the way, it's dot, dot, dot to 4, because I don't know how long down the line until I hit this general, and dot, dot, dot after, saying this goes forever. The summation notation is pretty much just using that general, but also then identifying your starting index, which is n equal 0 and going forever because of the dot, dot, dot. Isn't only if 0, doesn't that give me an x to the 0 and a positive? So we're good? Okay. Now, you can notice, by the way, hey, cosine and its polynomial are even powers. That makes sense. You're not going to fit an even function cosine with kind of even odd polynomial. It's got to be an even polynomial. Say with sine being odd. All right. E to the x. Is e to the x even, odd, or neither? Neither. So I would expect there to be a little mixture of both parts. Would you please do the McLaurin for e to the x?
You write them in forms, did you do t of x or t of 0?
T of x. It's supposed to be a polynomial that fits for any. Okay. This one's the easiest. How are you doing here? What? Did you hear that? Oh, okay. We're just walking all around. So what's the general term here? X to the n over n factorial. No alternating negative. That's nice. Okay. Therefore, the summation is also x to the n over n factorial, and the starting index would have to be. Okay. All right. Now, that just gave you a way to estimate e to the first. If I asked you to tell me what's e, well, that would mean that e to the first is 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. That's equals. Okay. 2, 2 and a half, 2 plus a 6, a half plus a 6, is 2 and 5, 6. It starts to converge. That's how he's calculating. Okay. Would you? Now, a great question would be, is what Jeff just asked, is, all right, I get E, I see sine and cosine, they're weird, they're hard to figure out, they're abstract, they're transcendental, yeah. Why would you want to do a polynomial series here? I don't have a hard time estimating what this is at 2 or anything. That seems like that would be complicated to make it a polynomial, more complicated, yeah? Good question. I agree with you. So the deal is this, though. With a small change, I could call this just by substituting a negative x into my McLaurin for a positive x. And you might say, I still look at it, that's also easy. But what if I integrated this? Now, if this is a series, then if I integrate that, then it too will be a series. But what's the antiderivative? Natural log of 1 plus x. You just found a way to estimate natural logs.
Absolutely.
What if it had been, let's pause these, 1 over 1 plus x squared? What if it had been that? What's the antiderivative? Arctangent. And you have a way to do arctangent. Now you might say, who cares about arctangent? But what if I said, what is the arctangent of 1? Pi over 4. And it is all this stuff over here. And therefore pi is 4 times 1, 2, 3 terms. I got pi, just like that. Yeah. So that, although it seems like 1 over 1 minus x is a no-brainer and not necessary for us, it is actually the Abraham of series. It leads up to all these different branches all the way through, okay? So, would you, therefore, please find the series for it? It's important. It's important. Now, this one is sloppy. You start to get a little bit gross on the derivatives here. It's just be careful. If I were teaching this to a lesser bunch, I would make you go off to the side and make a table of the derivatives to keep it organized. But I gotta be honest with you, I think you'll be just fine if you, in an organized way, do the derivatives in your Taylor. Just make sure that you're not writing slop. You know who you are. Because stuff gets lost in this case if you write slop. Now, you might think of this, by the way, as 1 minus x to the, actually, maybe we should go off to the side. Are you worried about making a mistake here? Let's do this together, shall we? So, what's the derivative on that? Negative 1, 1 minus x to the negative 2 times chain rule, negative 1, okay? So you can see it's a little gotcha there. That then would be something like positive 1 minus x to the negative 2, right? All right, x minus 0 to the first over 1 factorial. What about the second derivative? Negative 2, 1 minus x to the negative 3 times another chain rule negative 1 over, or times x minus 0 squared over 2 factorial. This then amounts to positive 2. You follow? Okay. Still not there yet. I'm not convinced we. Yeah. Okay. Next. Negative 3 times 2 times 1 minus x to the negative 4 times the chain rule negative 1. X minus 0 to the third over 3 factorial. Now the negative goes away. And you have 3 times 2 times 1. And so on, x minus. So, well then, let's do a little bit of cleanup. This is 1. What is this guy at 0? Sorry, this should be at 0. It's at x equals 0. This is. I really turned you around if you can't answer 1 minus x when x is 0. Good job. That's great. Way to go. Okay. 1 x to the first over 1 factorial plus. Now this is 2 times 1 x squared over 2 factorial. The next one Negatives went away. It's 3 times 2 times 1, or 3 factorial x to the third over 3 factorial. So what do you reckon the next one is? X to the fourth. It is the cleanest of all series. It is just 1 plus x squared plus x cubed plus dot 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 dot. What's the general term? X to the n. In summation notation, it is x to the n over, or starting at rather, 0 and going forever. Now, how do you like that? What do you think about that? Think about it. Sure. Okay. I've eliminated the critical thinking out of it. Okay. So you're telling me, does this wash this? These are the same. This equals this. I just proved it does. What if x equals 2? Yeah, not so much. Okay. But what if x equals a half? Well, then you'll say yes. Does this look familiar? I'll say this. Sound familiar? Okay, now this is a geometric series, right? This is geometric with an a of 1 and a common ratio of x, and if you took 1 and multiplied by x over and over again, wouldn't you get? And it's true, but it only is true only if r, which is x, is less than 1. It's only true in an interval of convergence from -1 to 1. Okay, now that's all for later, but that's a good start. Wow, questions on the homework? No? Okay, turn it in.
What?
Just all right, we'll do extra practice on. We'll do extra practice on Monday, so it won't be a lesson. You just have time for questions. I'll put the key up to the extra practice for that to help. Copy faster, yes, it'll help you use it judiciously. Those are more. Okay, I will post the key online so you can get it.
Were there rare, like, 10 of us who've done it?
Yeah, but not weekend ahead.
But the rest of it,
It's all just shit. That's what I do at the
Thank you so much.
Sure, no problem. Okie dokie. Oh, I forgot to stop my recording. Bye, Elizabeth.